explore the impact of automated theorem provers on math and on our understanding of mathematical proof. Logicians laid the groundwork for computer provers early in the 20th century. Mathematicians such as Bertrand Russell and David Hilbert set to putting math on a formal logical footing. In 1908, Henri Poincaré disapproved of their formalism, presciently stating that one could imagine a machine where one would put in axioms at one end while getting theorems at the other end, like that legendary machine in Chicago, which pigs go into alive and come out transformed into hams and sausages. By contrast, on hearing that computers had reproduced his work, Bertrand Russell said, "I am delighted to know that the Principia Mathematica can now be done by machinery. I am quite willing to believe that everything in deductive logic can be done by machinery." Early automated theorem provers were developed in the 1950s. Scientists at Rand Corporation worked on a theorem prover partly because they thought it would be easier than doing AI for chess. The logic theory machine had proofs for many theorems from Principia Mathematica, including one that was originally in error. By 1960, Wang, a logician at Harvard, had a program that could prove all the theorems from the Principia in less than a minute. However, computer-assisted proof became a lot more interesting and controversial in 1976, when computers were used to prove the four-color theorem, a conjecture proposed in 1852 that says that you can draw distinct regions on any map with only four colors. Appel and Haken proved the four-color theorem by subdividing the problem into 1936 different cases and showing by computer that each of these maps had the property. They then showed by hand that any attempt to make a larger map as a counterexample would fail because it is in fact composed of one of these smaller maps. In 1996, Robertson, Sanders, Seymour, and Thomas reduced the number of different cases to just 633. Both groups had built a custom program to check the many cases of the problem. In 2005, George Gauthier had used a computer program to develop the entire proof with a general-purpose program called Coq Proof Assistant. The four-color theorem is famous for being the first long-standing mathematical problem to be resolved using a computer program. George Gauthier said that in his computer check proof of the four-color theorem. There are a couple other examples of famous theorems that were resolved using a computer. In 1978, McCune used a computer to solve the Robbins problem, which had been unsolved for 60 years. It says that a set of three equations is equivalent to Boolean algebra. Burris, another mathematician, was able to verify it and translate it into 3 pages of mathematics in the more familiar, less formal style. Robbins had formulated the problem as a young graduate student and lived to see it solved by a computer. In 2014, Konev and Lisitsa proved a case of a famous theorem proposed by Erdos. They say that it is probably one of the longest proofs of a non-trivial mathematical result ever produced. Its gigantic size is comparable, for example, with the size of the whole Wikipedia, so one may have doubts about to which degree this can be accepted as a proof of a mathematical statement. Mathematicians are conflicted over the role of automated proof in mathematics. Responding to the proof of the four-color theorem and its many cases proved by a computer, Hirsch says, "I do not find it easy to say what we learned from all that. The present proof relies, in effect, on an oracle. And I say down with oracles. They are not mathematics." And Donald Mackenzie on the same subject wrote, "Indeed, a very considerable but entirely uncelebrated achievement of the work whose history is reviewed here is that it has shown the practicality of formal proof. Paradoxically, however, in mechanizing formal proof, the automation of mathematical reasoning has potentially reopened questions of what proof should be taken as consisting in. So are proofs a matter of certainty, or are they a matter of human understanding?" Robertson writes, "However, from a practical point of view, the chance of a computer error that appears consistently in exactly the same way on all runs of our programs, on all the compilers, under all the operating systems that our programs run on, is infinitesimally small compared to the chance of a human error during the same amount of case checking. Apart from this hypothetical possibility of a computer consistently giving an incorrect answer, the rest of our proof can be verified in the same way as traditional mathematical proofs. Robertson was defending his program, which was verified for validity itself, and he was in favor of using certainty as a measure of proof. On the other hand, Thurston is in favor of using human understanding as a measure of proof. He wrote that, however, we should recognize that the humanly understandable and humanly checkable proofs that we actually do are what is most important to us, and that they are quite different from formal proofs. For the present, formal proofs are out of reach and mostly irrelevant. We have good human processes for checking mathematical validity. There are lengthy proofs written by hand, and there actually are short proofs that were discovered first by computer. Automated proofs aren't unique for being hard to verify, and sometimes they can be brief and inventive, which are things that we normally associate with human work. On Andrew Wiles' famous proof of Fermat's last theorem, Claude wrote that the proof is extremely intricate, quite long, over 100 printed pages, and only a handful of people in the entire world can claim to understand it. To the rest of us, it is utterly incomprehensible, and yet we all feel entitled to say that Fermat's last theorem has been proved. On which grounds? We say so because we believe the experts and we cannot tell for ourselves. On the Robbins problem, which has a proof that fits in 3 pages, discovered by a computer, the proof depends upon a successful search among a realm of possibilities and the skillful application of pattern recognition and the application of axioms. This is very close to the work of a human mathematician. EQP, the program, being able to understand and handle many possibilities and great depths of parentheses, has an advantage over her human colleagues. I understood EQP's proof with an enjoyment that was very much the same as the enjoyment that I get from a proof produced by a human being. Kaufman wrote that regarding the Robbins problem proof. Is there a future of human and computer collaboration on proofs in mathematics? The modern mathematician Russell wrote, generally, the problem the automated theorem prover faces is that the derivation is too complex for the theorem prover to discover in a reasonable length of time. Therefore, an interactive theorem prover should provide an environment where the user can structure the derivation into a set of sub-derivations. This kind of structuring is just what most theorem provers find difficult. The user can then direct the theorem prover to detect each sub-derivation independently. Some see this as the future of mathematics. Ronald L. Graham of AT&T Bell Laboratories suggests that the trend away from short, clear, conventional proofs that are beyond reasonable doubt may be inevitable. The things you can prove may be just tiny islands, exceptions, compared to the vast sea of results that cannot be proved by human thought alone, he explains. This is a burgeoning field in math and in computer science. Some hope that automated theorem proving will have applications in checking the reliability of mission-critical software systems. An array of publications and growing familiarity with technology in a new generation of mathematicians promise much more to come. Thank you.